Hello Python programmers. Let's take a look at Numpy. Here's a review of the data structures inherent in Python, some of them. Numpy data structures are analogous to lists in some ways. We use the square bracket notation. Elements of a NumPy array are mutable. They can be changed. And you'll see a lot of similarities as we go along. Numeric Python was developed in response to some performance issues, among other things, inherent in the list data structure. It ended up taking a very long time to process large amounts of data, longer than it should have, because of the inherent way that data is stored in a Python list. And instead of abandoning the Python list, which would not have been expedient because there was a huge code base out there and it was a well understood data structure, the Numpy library was added as an adjunct to provide faster processing while giving up some capabilities. I think the one that jumps out at me the most is that a NumPy array is homogeneous. And it really doesn't have to be, but it by default is homogeneous. Whereas a list by default could be heterogeneous. And if you're creating complex data structures to model things in the real world, it's very rare that anything in the real world consists of a whole bunch of identical data types. If you're modeling a person, they have a name and an address, and they have many characteristics that are not integers. Therefore, a list might make sense if you're storing that kind of data. But if you're processing large amounts of numeric data, for example, an image, and that could be a JPEG or even a video, then that data is numeric. And it would make sense to model that with a data structure that works well on numeric types, and that would be something like NumPy. When we use the term axis, just think of the term dimension. I think we all learn what dimensions are kind of as we progress through school. We all know there's 3 dimensions in the real world. Maybe the 4th dimension would be time. But sometimes we see the word axis and it gets confusing. I always just substitute the word dimension. Don't forget your import statement. And I keep harping on this because sometimes you see a code snippet on the web or in a book and they omit the fact that you need the library. If you see this error enough times, then you recognize what it is immediately and you can fix it. We index into a NumPy array using square brackets. We can concatenate the square brackets to the left of the array name, to the right of the array name, and we can define multiple axes or dimensions that way. Two dimensions are reasonably easy to deal with. We can represent that on a piece of paper or a screen. Rows and columns are typically the labels that we use. But when you get above 2 dimensions, it's very difficult to represent graphically, and a lot of times just conceptually even becomes problematic. But maybe I provided one here that would help. If length, width, height, and time could be conceived as 4 dimensions and could be modeled in a NumPy array. And that, I think, at the outset makes sense, but it rapidly becomes very difficult to conceptualize when you have something that has 4 dimensions stored inside of computer, and then you've got to, at the same time, understand that with your brain. And I don't have the skill to do that. I'll be the first to admit my brain falls apart when I try to grasp the concept of a 4-dimensional thing inside a machine. Maybe I'm thinking about it too hard, but we're going to stay away from things that complex. Syntax, if we use the square brackets, we get what we think of as an array or a list. If we separate two of those by a comma, we get two arrays. But if we wrap that whole thing in parentheses, we get a tuple, and each element of the tuple is an array. And then if we drop the tuple notation and wrap those two arrays in another set of square brackets, we're creating one big array with two dimensions. And it's just something that takes a little bit of study, and eventually you become accustomed to reading it. And that's why I'm so big on printing out the data types of things and breaking things down into smaller parts to get a good grasp of what we're storing and how we're storing it. Creating an array from a set of constant values is straightforward. This example, we're calling a function called array, which is part of the NP class. And we pass it one argument, that is the data to be used to create that array. And then we pass it another argument optionally, which is the data type that we want to use when we create that array. Now, if you don't pass the second argument, it will infer from the data what the data type should be. I'll say that again. The second argument in this example is optional, and Numpy will look at the data and make an informed decision as to what kind of data is being stored. Int32 means that we are storing 32-bit integer values as each element of this array. Remember, the thing is homogeneous, so we don't have to specify the data type of each individual element. We simply specify one data type, and it is used to apply to all the elements. A 32-bit integer, I don't expect you to memorize the range, just have a feel. Your takeaway should be that a 32-bit int goes from plus or minus 2 billion. So minus 2 billion to plus 2 billion is a reasonable analog for what can be stored in those values. In this example, we are taking those two arrays that you saw in the previous slide, and we're wrapping them in square brackets, meaning we're creating one array, each element of that one array consisting of another array. And what we called this in the past was a list of lists, and that still applies. Behind the scenes, this array function, np.array, is taking a list of lists and creating a NumPy array from that. Here are two slightly different examples. So take a close look at this and make sure that you can differentiate what's going on here. Remember, we do a lot of reading of other people's code, and it's important to be able to understand the intent and the functionality of what we're reading. In this case, the first example of the call to array is creating an array from a list of lists. Now, each list in this list of lists is one element. So when we encircle the 100 with square brackets, that's a list of one element. Then we separate that by another list of one element using a comma, and finally we wrap the entire thing in square brackets. So a list of lists, and each list is one element inside that big list. The second example, same data, 100, 200, 300, 400, 500. However, it is a list of integers. Each element in this list is an integer. And what you're going to get as a result then is a different interpretation by that np.array function to create the NumPy array. Now I have JupyterLab running, and I've got an empty notebook that I'm going to use just to do some illustrations. I created a cell at the top with just my import statements in it. The NumPy library is imported and then aliased as NP by convention. So this is a common way that many developers use to refer to NumPy once they've imported it. They shorten it to NP. I'm going to take that code off the slide and then just look at it a little bit. And in a brand new cell, I'll simply paste in those 2 lines of code right off of slide 8. And let's just print them out. And I want to see how the array function interpreted those data sets. So I'll print B and I'll print C. Make sure that you run the import statement. It only needs to be run once. It gets flagged with that little number 1 next to it, meaning that it has run and it was actually the only thing to run at this point. And then I can run the second cell as many times as I like, and I can be comfortable that NumPy has been imported, and it will be there for me as long as I need it. And the print statements print slightly different results. The first print statement of the B array is 1 column and 5 rows. The second print statement of the C array is 1 row with 5 columns. You can see that it interprets the data as each element in that list is a row. So the first list of lists had 5 rows. The second list had 1 row with 5 columns in it. Same data, but different results. And then let's go back and try to print an individual element. So to get some practice slicing into this array and getting out parts of it, let's print out C sub 1. And if I saw you on the street in Clifton and I said hi to you and I ask you what this would print, you would tell me that it prints the second element. Let's find out. There's the 200. And if you go back to the reference for B, where we printed B, let's add another print statement below that, and let's print out B sub 1. Whoops, got his extra 0 in there. What are we going to get when we print B sub 1? We're going to get a 200, but it's in square brackets, meaning that it's the entire list. So you can see that we can index into these NumPy arrays using square brackets and strategic choices for the element numbers. If I select B sub 5, whoops, that's going to fail dramatically because there is no B sub 5. We index from 0. The 0th element is 100. The first element is the element 1 is 200, so on, and that should give me a dramatic error. And there it is. The error is pretty good. Index 5 is out of bounds for axis 0 with size 5, meaning that there are only indexes available from 0 to 4. There is no 5. Let's clear that out. I don't like having that error message there. I'll put a comment there, and I will say this fails. Run it again. Okay. Back to slides. In slide 9, I'm dumping a larger example on you. And in this case, I've got a line of code that I know will fail because I'm improperly providing values to the np.array function, and I'll talk about that in a second. And then I'm creating a couple of 2-dimensional arrays that we can manipulate. And I'm just going to copy this code right off the slide, and then back into my little test mule here. Let me clear out some errors. There we go. So I'm pasting in a new cell at the bottom of this little blank workbook, notebook that we're playing with, and the code right off the slide. Before we look at the code that works, let's look at the code that doesn't work and talk about why. I'll uncomment the first line of code in that cell. And we know this is going to fail. Let's examine it when it fails. The error says field elements must be 2 or 3 tuples. Got 5. What that's trying to tell you is that the second argument to this function is supposed to be the data type, and that's not what you provided. Our first argument is 1, 2, 3, 4 wrapped up as a list. Our second argument is 5, 6, 7, 8 wrapped up as a list, which is supposed to be the int32 parameter or whatever data type you'd like it to be. So that's just not going to work. And if you looked at the line right below that in the slide, you can see how I chose to fix that by putting the first argument in one big list, as we saw in an earlier slide. And then the second argument is correct, np.int32. So let's comment that back out again because it's just a troublemaker and we won't look at it anymore. The next set of 3 lines is my attempt to create a 2-dimensional array and then specify that the individual elements of that array should be int32. Remember, whenever you see int32, just think plus or minus 2 billion and no decimal places and you'll be fine. This function array sends back to me a Numpy object, the reference to which I'm storing in array ARR. And this Numpy object has a property called shape. Very helpful because we can look at the shape programmatically to tell us how this array has been created. In this case, it's got 2 rows and 4 columns. And let's add one more print statement to this just to print out the array itself. And you can see it's 2 rows and 4 columns. The first row is a list of 4 numbers. The second row is another list of 4 numbers. And the syntax of that output from that print statement looks very familiar to us. You can see that there's a list inside of a list, or 2 lists inside of a list. Notice that the data type of the shape of that Numpy array is a tuple. Again, a numeric or a data structure we can use to store numbers. And the difference between a tuple and a list is that the tuple is immutable. You can't change the values of it. That makes sense then to store the shape as a tuple because we wouldn't be able to change the shape of something once we've created it that easily. In our second example in this cell, we wrapped the 2 lists in parentheses. Take a close look at that. Instead of a list of lists, it is a tuple of lists. And the point being made here is that Numpy can deal with that just as well. It's fine with that. So you can send the array function a list of lists or a tuple of lists, and it will, in both cases, be able to create a Numpy array from that. Let's do one more thing before we leave this example. I am going to print at the bottom of this cell that we've got going here arr.dtype. arr.dtype. dtype is data type. And that tells us that everything stored in that Numpy array is an int32. We already knew that because we specified int32 when we created that array. just it is possible to go back and interrogate that if you have an array that you're not quite sure about. Let's do another thing. Maybe I don't want to let go of this cell so easily. Let's take out the second argument in the call to np.array. Now I'm passing it a tuple of lists, and I'm still going to get 2 rows and 4 columns, but I'm going to let NumPy decide what the data type should be. And if you're following along, you should probably realize it's not going to make any difference since all of these are integers, that I'm still going to get int32 as my type. Let's find out. And I still get int32. Let's play a little game though. Let's make one of these a floating point number. Let's make this 8.5. Now my 8 initializers are 1, 2, 3, 4, 5, 6, 7, and 8.5. And it's not majority rules type decision here. Let's find out what we get. Now I get a float 64, which means it's a 64-bit floating point number. It's a data type that supports decimal places. And I'm not going to get into the upper and lower bounds of a float 64. I just want you to recognize that when you see that float 64 data type, it does support decimal places. Now let's try one more since I've got you here. Let's put quotes around this. We're saying now that we have 7 integer initializers and 1 string. Again, since it's not majority rule, what's going to happen? There you go. So now I get U11 as my data type. U11 doesn't tell you much at all, does it? That means there is a string somewhere in that list of initializers causing NumPy to create an array of Unicode character strings, and they decided that 11 would be the limit of each of those individual strings. So the U means Unicode, and the 11 means 11 characters wide. Unicode is a character mapping strategy that lets computers represent a very, very wide set of English or of spoken languages. Because we had something called ASCII in the past. You may have heard of ASCII, which was okay, but it only supported English. And we found out pretty quickly that not everybody spoke English, so we created this new strategy called Unicode. And it lets us store character values from not just English, but kanji and many other different languages from around the world. So wherever you see U, think Unicode and think strings. We beat that one to death. Let's go back to our slides again. Slide 10. We're going to create an array. We're going to reshape it, and then we're going to print it out. This is another example just of basic array manipulation in NumPy. And remember, we've kind of switched gears on our terminology. We used to say the word list, but now we're just saying the word array. And when we had no knowledge of NumPy, it made sense to call it a list. But then we were learning about NumPy, and they call it an array. But it, again, has a lot of overlapping terminology and concepts from the list structure that we talked about in previous weeks. In this example of code, again, I took it right off the slide. That is slide 10. Pasted it into a new cell in JupyterLab. The first thing that we do is create a range of integers from 0 to 19. That's what the A range does. So we're making a call to a function called A range. I guess we should probably just call this an array. An array with a range of integers. And then we call the shape function that takes that 20 element linear one-dimensional array and rearranges it into a 4 by 5 two-dimensional array. When we run this cell, you can see the shape of our new array is 4 by 5, 4 rows, 5 columns, and the values are from 0 to 19, courtesy of that A range function that we called. The takeaway from this is the ease of creating an array that's pre-initialized and then shaping it into the desired shape. Out of curiosity, let's try to shape it into a three-dimensional array. What if I say 4, 5, 6? 4 by 5 by 6. I'm saying I want length, width, and height, or some other quantity that's represented in 3 dimensions. And if you're following along, you're screaming at your monitor because you know this is going to fail. The error is cannot reshape array of size 20 into shape 4, 5, 6. We asked for 20 elements in our initial array when we called A range, and then we said take that 20 element array and make it into an array of size 4 times 5 times 6. 4 times 5 is 20, so that would be 120. We can't take 20 elements and squeeze 20 elements into 120 elements. It's physically impossible. So we have to make a decision. We can't do what we need to do given only 20 elements. How about if we just make this 120 elements? The numbers match now. 4 times 5 times 6. 4 times 5 is 20. Times 6 is 120. I hope. I'm doing this in my head. And we're providing 120. Let's see what we get now. There we go. This gets rapidly out of hand because we're trying to represent when we print a three-dimensional thing in 2 dimensions, and my head starts to hurt. If you have the mental flexibility of mentally representing 3 dimensions in your mind and grasping that concept when they're put on a 2-dimensional screen, that's terrific. I don't have that skill. I struggle with this. But in this class, we won't do anything beyond 2 dimensions except generally talk about it. I also gave you the shape of that array. As you hopefully expect, it's 4 by 5 by 6 because that's what we use when we called reshape. So we've demonstrated how to create a range of numbers and store them in a one-dimensional array and then reshape that array into multiple dimensions. What if we provide too many numbers? Let's say we provided 121 numbers in our range, but we know that there are only 120 spots in the reshaped array. What will happen to that extra number? Let's find out. Again, we got a conflict, which is a good thing. Python tells us what you're trying to do doesn't make sense, therefore I won't do it for you. Cannot reshape array of size 121, a linear 121 element array, into a 3-dimensional 4 by 5 by 6 array. Doesn't make sense. Doesn't work. Slide 11. We can do some slicing. Remember how we sliced up lists? We can also slice up NumPy arrays, which are similar to lists. And we can use commas as dimension separators in the square brackets. And we can specify a range by wrapping numbers around a colon. So this syntax should look familiar based on the exercises we did with list slicing. And I will grab this little snippet of code. 3 measly lines of code. Back to Jupyter Lab. Let's make a new cell. Print it out. The first thing we do is generate a one-dimensional list from 0 to 99. Then we reshape it to a two-dimensional array of 5 rows by 20 columns. And then we print that out to make sure that we get what we think we get. It looks wonderful and beautiful. Finally, we demonstrate the slice. So slice it up. The important thing for you to be able to do is understand the significance of the comma and the significance of the colon. The comma then is separating dimensions. This is a two-dimensional array to begin with, so we put a comma in there to separate rows from columns. And then we do a slice on the rows by saying 0:2. Interpreting this slice, let's do the easy one first. The comma 2 says I want column index 2. It's row, comma, column. Column index 2, that's physical column 3 because we are 0 indexed. And then the row slice is I want the first row and the second row stopping before you get to the third row. And we get as our result 2 space 22. Notice it's rendered as a one-dimensional thing with 1 row and 2 columns. So what we get back from this slicing operation is 1 row and 2 columns. And let's print that out. Let's say new array equals, and I will simply duplicate the slicing operation that I showed you a moment ago. And then I want to investigate that new thing a little bit. So new array, let's print it out, and then let's print the shape of it. And we can look up above and see that to print the shape, it's just dot shape. Print new array dot shape. And the shape is kind of funky. It's a 2 comma. Make sure that you can make sense of that. Back to the slides again. We are moving right along. Slide 12. In this slide, I'm merely emphasizing zero-based work. And it's a big deal to us as programmers because it's not a big deal to civilians. Nobody counts things from 0. And when you jump into this world of programming, you have to mentally condition yourself to count from 0 instead of counting from 1. This example then just shows you what happens when you specify a 0 as an index. The last example is kind of neat. We're using a -1. And we've still got this 4 by 5 two-dimensional Numpy array. And if we say that we're slicing it -1, -1, we're asking for the last column of the last row, which is pretty neat. One of the big advantages of Python is the ability to do operations against large structures of data without explicit loops. We could do this in any language, but in some languages we'd be reduced to writing a for loop inside of a for loop and then adding a for loop for every dimension that we had in our data structure. But Python lets us do it by passing an operation. So let's take this code and spend some time on it because it is so interesting. The first thing we're doing, as you recognize, is creating a one-dimensional array of 20 elements, 0 to 19, reshaping it as a two-dimensional array of 4 rows and 5 columns. That's all good. Print it out just to make ourselves happy that we know what it is. Practice a slice. There may be a problem on this line of code. I think there's a spurious character in there. Oh, there isn't. That's odd. I'm going to take that out because it makes me nervous. Do I get the same thing? Yeah, I do. All right, I don't know what that little guy was doing in there. Then I illustrate a one line of code solution to multiply every element in that array by some value. Now I could do a for each inside of a for each to accomplish the same thing, but we don't want to do that if we can shorten it up this way. And if you were to do this in more advanced applications, you can see that you can build on this to do very complex expressions rolled up into one line of code. We're not going to be doing any of that here, but this is just the foundation for some really slick programming that's possible. And then when I printed out my result, I was showing off a little, and I just printed one row. So I use -1 as my index. And since I've got you here, let's try to do this as, so to speak, a brute force for loop. Let's replace this one line of code where we're multiplying everything by 42 with several lines of code that do the same thing. So through the magic of editing, so you wouldn't have to watch me type it in, I wrote a few lines of code to simulate what we'd already done in one line of code. And I chose to use two loops, one loop inside of another, two range objects, and then finally an assignment statement that commits a multiplication. And the times equal might not be comfortable for you, so I can just write this a little more traditionally. How about that? Multiplying each element in that Numpy array by 42. Hopefully you'll look at the example I gave you initially and realize that one line of code is just so much more elegant and eventually easy to understand than this brute force method of implementing a nested loop and then doing multiplication, element-wise multiplication on everything in that array. Result is the same. I don't know if one is optimized more efficiently than the other. I couldn't tell you. They probably end up taking the same amount of time. Although, since I have more code usually means more time. All right. You can see this produces, they both produce the same result. There are the two printouts of the last row. Back to the slides again. On slide 14, we're looking at Reshape. And we're pointing out here a common mistake that people make, and this is another mindset issue you have to develop, because calling Reshape does not necessarily do what some people think it does. It creates a new array and returns that to be used in an assignment statement or another expression. It does not affect the target array. The target array remains the same. So let's look at how we're using this. Back to Jupyter Lab again, brand new cell, paste in the code. What you'll have to notice here is that we're creating a list called a list, and then we're using that list to create a NumPy array. Okay, so we have our friendly NumPy array that we've grown to love in the last half hour. We print it out just to make sure it is what we think it is. We print out the shape of it to make sure it's shaped the way we think it is. And then we're going to make an attempt to reshape the array. for some devious purpose. We're going to go from a 3 by 4 to a 6 by 2. And that's okay because they both have 12 elements. We won't get any error message going from a 3 by 4 to a 6 by 2. If we print it out, though, you're going to see in this print statement that it doesn't affect a change on the original array, and it appears that nothing happened at all, which could be a little disconcerting and cause you a lot of debugging time if you're not sure what's going on. And then below, at the bottom of the cell, we do pretty much the same thing, except when we call Reshape, it's going to assign the value returned by Reshape over to our variable b, and then b will indeed be that new 6 by 2. So let's print this out and take a look, run the cell. And you can visually verify that the first call to Reshape did something, but the something that it did got discarded. And then the second call to Reshape did something, and the something that it did got stored to our variable b. Notice there are no warnings or error messages when you do this because it's doing exactly what you told it to do. It's performing a reshape, and it's handing back to you a reference to that newly shaped thing, but you're not storing that reference anywhere. You're just ignoring it. And then in the second example, you're grabbing a hold of that new reference and storing it in your variable b. It's something you have to experience probably to learn how to deal with. But hopefully if you get to the point in your code where you're just certain that something should be changing, but it's not, it could be because you're not storing that changed thing. You're just throwing it away. And if you look at np.reshape, it will tell you that. Through the magic of editing, I brought up the authoritative documentation for NumPy. We're looking at numpy.reshape. You have to read this carefully, but if you scroll down a little bit, it says that this function returns the reshaped array. There's your visual cue that whatever you want this thing to do, you better catch it when it sends it back to you. You better use it in an expression like an assignment statement. The top here is a little bit misleading. It says array to be reshaped. What it doesn't say is that it's not reshaping that array. It's creating a newly reshaped array and sending it back to you. So whatever A is in this case is unchanged. It does not get mutated. Something to be careful about. Slide 15. We can't iterate over rows. I showed you this just a moment ago when I wrote that reimagination of that multiplication operation. So you can iterate over rows in a NumPy array by using a for loop. This has a lot of value if you're not really sure how to write a complex expression. It's okay to fall back on this. Just be aware there's probably an easier way. And again, this is new to us. We're not whiz-bang, super-duper Python programmers, so unless I ask you to do something in an explicit way, then it's okay to do it the brute force way. That's fine. Now this particular one, and I want to talk about it some more, so I will take it back over to Jupyter Lab as we are doing. This particular example iterates over rows. Each pass through this loop, I have one row to process. I process the first row, and in this case my processing is adding up all the elements in the row. Then the second time through the loop I process the second row and add up all the elements in that row. This then is a slick way or a convenient way a convenient way to iterate over rows in a two-dimensional NumPy array. If you have a cause to use some logic that processes a row at a time, then this is the way you might do that. If you're not sure how to even get there, then fall back on your search engine, NumPy, iterate over rows, whoops, not wows, iterate over rows in an array. You will find plenty of code snippets that will get you started on that. Slide 16. You may have an instance where you want to iterate over everything, element by element. You don't care if they're in rows or not. So sometimes your data is just stored in a two-dimensional array, but it represents just a stream of numbers. And you can use the flat function to take a 2D or a 3D or a 4D NumPy array and convert it into a one-dimensional array. This is another example of being sure that you catch whatever that function sends back to you. And I've got my code in JupyterLab. From the slide, I'm calling flat. Flat doesn't change ARR in this case. Flat doesn't change my original array. It creates a new array that is a one-dimensional version of what was in ARR. And let's put another print statement in here just to demonstrate that. We'll put print ARR. Run that little guy. And we can see that ARR is still a two-dimensional array running from 0 to 19, but B has been flattened out and it is a one-dimensional array running from 0 to 19. Be careful again to have a good understanding that which functions operate on their array and which functions return a new thing for you to save. Okay. Slide 17. This is to get you thinking about what Python will do for you already. There are many, many functions to operate on NumPy arrays. If you want to do something to a NumPy array, chances are it's already been done, and in most cases it's been implemented as a built-in part of the Numpy library. So in this case, I'm going to get the maximum value in that array simply by calling amax. Again, let's take our code off the slide and make ourselves a cell. You should be able by now to look at this code and tell me what it will do. If you know what amax does, which is return the maximum value in that array, we should be able to predict that since we're creating an array out of a range that goes from 0 to 19, the shape of it is irrelevant, doesn't make any difference, but it should print out 19, right? Hallelujah, it does, because the last element in that array is 19 since the elements are ascending order from 0 to 19. So if I want to do something to an array, I can probably find a little bit of code that will do that for me. Slide 18. Random numbers are useful for testing purposes. Often we need to cobble up some data for a simulation, and we need to cobble up the same data but random data over and over. So There is a random function built into NumPy. There's also a random number generator built into Python, which I suspect NumPy uses. And we can define a range that we want to generate, and then we can store that into an array at the same time. And voila, we have an array full of random values. Let's take this code, Control C, back to, oh, I'm lost. Where am I? There we go. This little snippet of code, which is so wonderful, creates an array of random numbers, 2 rows by 3 columns, returns it back to us in the form of a reference, which we catch in ARR and store in that variable name. So we've got a copy of that created array. What if I did this? What if I was just not paying attention and I just did that? What if I said np.random.rand paren 2 comma 3 close paren? And what if that was the only part of that code? What if I didn't do anything else? Well, this would still work. It would still generate the array, but then it would just throw it away. Because when it sent me the reference back, I didn't catch the reference, I didn't store the reference anywhere, and I'm sunk. That's why I need to catch it with that assignment statement. When we run this, there's my answer. The first value in that array, first row, first column, is 0.175333415. And what does it say on the slide? On the slide, it says 0.987. And we know, of course, that is because we are generating random numbers. You can specify the seed of the random number generator and be guaranteed the same random numbers each time you run your code. That is possible to do. We won't do that here. I'll leave that as an exercise. But what if these numbers are not exactly what we want? Perhaps we want integer values. I mean, these are nice floating point numbers. They're pretty and they have lots of decimal places. But what if my simulation requires integers in my NumPy array? How about if I brute force a couple of loops here? So for I in range 0, 2, colon, for j in, whoops, range, I'm not typing very well, range 0, 3, colon, ARR, I, j equals, and I want, how about int, and I'm going to say ARR, whoops, paren, ARR sub I, j times 100, and then let's print out ARR. I'm also going, well, let's just leave it that way. Okay, does that work? That didn't work. Typo, right? Yeah, INT, I got carried away. Let's see if that works. There we go. We multiplied the element by 100 to give it a couple of places to the left of the decimal point, and then we converted it to an integer. So I have a very nice array with integer values instead of all those nasty decimal places. There's still floating point numbers because when I created ARR, I created it using floating point numbers, and the NumPy library detected that, therefore it made them all float 64s. So they are, technically speaking, they don't have any decimal places, but structurally behind the scenes they are stored as floating point numbers. For those of you who are beyond the scope of this class right now, there are certainly other ways to accomplish this rather than an element-wise manipulation. of the array elements, but I'm going to skip over that now. Let's go back to the slides again. And you can see on that slide, I demonstrated something that I just told you I was going to skip over. How about that? Maybe I should peek ahead at my own slides before I talk too much. So in this example, I created my random number array of 2 by 3, 2 rows, 3 columns. And when I came to the realization that floating point numbers weren't going to get it done for me, I wrote one line of code that multiplies the entire array element-wise by 10 and then converts the entire array to integer. And this is a little bit confusing here because instead of saying int32 it just says int, but for us they're the same thing. And then I print that out and I can see that I now have an integer array where each of the numbers in the original random array were multiplied by 10 and then truncated. So one line of code does two things for me. Multiply each element by 10 and then convert the whole thing to integers. Pretty neat. This example, as a programmer, I adore this. I'm going to take the code off of slide 20, back to our trusty notebook again. And in this case, I'm going to create an expression where I'm comparing a modulo, the result of a modulo, with 0. And I'm going to store that into a new array. So I'm doing an element-wise evaluation of each element by modding it by 2 and then comparing it with 0. Now the upshot of modding by 2 and comparing with 0 is going to tell me whether or not it's odd or even. And then I'm going to store that element-wise mod by 2 compare with 0 into a brand new array called temp. Then I'm going to use temp as a map to select only the true values, which are going to be the even numbers, from my original array, which to me is just amazing. I love to be able to do this. The first thing I print is my true-false array. Remember, that's the result of element-wise mod by 2 compare with 0. And that's just an array of trues and falses. It's the same shape as the original array. And then I use that new array, that list of that two-dimensional array of trues and falses, as a selector. If the value is true, then I want the corresponding value from my original array. If the value is false, I don't want that corresponding value. And that sends me back a third array called evens. When I print out evens, I get only the even numbers in my initial array. So this does bear some study on your part because we're doing something dramatic in that we're applying an expression across each element of an array and then using that result of that expression to create a new array. Let's flip the script. What if I just want the odd numbers? All I have to do is change that expression. Now I'm saying take the element mod 2, and if the result of element mod 2 is 1, that means it's an odd number, and that will be a true value in my new array. So by flipping that from a 0 to a 1, I'm going to get only odd values in my array. And it's incorrectly named now because it's called evens, but it contains all the odd values. And what if I want only values that are divisible by 3? I can say mod 3, numlock key is on, sorry. Mod 3 equals 0. So anything divided by 3 evenly will have a remainder of 0. And then when I run it, I will only get values divisible by 3, 21, 24, 27, so on. This shows you the usefulness of mod and the tremendous power of applying member-wise or element-wise expressions across an entire array. If I get extreme, I can choose an excessively large number for perhaps 100. I'm saying that if my number, my element in ARR is evenly divisible by 100, then it will return a true value. And that should give me nothing, because nothing in that original array was evenly divisible by 100, since the only elements in the array were from 20 to 39. So take a few minutes to look at that, and if you've used other languages, you probably haven't seen anything like this before. And actually, you probably at an advantage if you haven't used other languages, because your mindset hasn't been cemented. And this kind of expression where you can apply member-wise operators and logical comparisons against, or relational comparisons against each element of an array with one line of code. I mean, we bypass totally that nested loop logic that we did earlier. It's just a tremendous way to do things. Slide 21. We have the capability of creating one array and then creating a second array and inserting it over top or overlaying it onto the original array. And this bears some study because we're doing all of a sudden operations on arrays of different sizes. And this bears taking back to Jupyter Lab. Let's go through this a little bit together. The first thing I do is create a 5-row, 6-column Numpy array, okay, and it's initialized from 0 to 29. I have 30 elements in my arrange, and I have 30 elements in my reshape. 30 equals 30, that matches up fine, no problem. I can print it out and you'll see that it's 5 by 6 and 30, 0 to 29. I could print the size of it, that might be mildly interesting. As you might expect, the size is 30, it has 30 elements in it, 5 times 6 is 30. The next thing I do is create another array. Here comes that syntax we saw at the outset of the presentation. Instead of one row, we have one column and 5 rows. And then here comes the magic. We can use slicing and indexing to put that new row into or overlaid on top of an existing, let's start over. Put that new column into overlaying an existing column of the ARR array. And we can do that with one assignment statement. This could be, we can say this replaces a nested loop perhaps. Maybe just one loop would do it. But we can shorten our code dramatically. And once we get accustomed to the slicing syntax, we don't have to write loops anymore. So maybe we shouldn't even be teaching loops, I don't know. You'll have to give me that perspective later on. If you look at the output, you can see that our B loop, which we actually didn't print. Let's print the B loop. Might help us visualize better. Print B. Let's remove some of these other prints. This gets a little cluttered. And let's print A and B. We won't print anything else. So print A. How about that? Let's print what's in A. A is a 5 by 6 30 element. Let's print what's in B. B is a 1 by 5 element. And then we'll print the result of putting one array B over top of the other array in the very first column. So that might be easier to visualize. And I did something wrong, and it's not called A, it's called ARR. My fault. Try that. There we go. The first time we print the original ARR array, the first column is 0, 6, 12, 18, 24. Then I print B, 0, or 100, 200, 300, 400, 500 in the form of a column. 1 column, 5 rows. And then after I do the overlay in this one elegant assignment statement right here, my B shows up as the first column in that original array. The original array then, that first column is gone, it's been erased, and it cannot be recovered. Let's examine the syntax of this wonderful assignment statement. Remember, we're using square brackets to index into ARR. And since ARR is two-dimensional, we need a comma to separate the two dimensions of ARR. And then we only want the first column of ARR, but we want all the rows. So we use a slice to represent all the rows. And the slice in this case is just a colon. We don't need an upper bound or a lower bound. That colon represents all the rows. Finally, we use 0, 1 to represent the first column. And that is the syntax inside those square brackets. Colon, comma, 0, 1 means all the rows and just the first column. The left side of that expression, the left side of the equal sign then, is a reference to the first column in ARR. On the right side of that equal sign is B. Okay, that just represents the entire array B. We happen to know that's 1 column, 5 rows. So the shape of one side of the equal sign is the same as the shape of the other side. That's the first part of getting it right, is making sure the shapes match. Let's print that out just to prove to ourselves that we're on the right track. Let's print let's see, ARR colon, comma, 0, 1 dot shape. Will that work? There's the shape right there. 5 rows, 1 column. And let's label that a little bit better. Shape of ARR is, comma, let's see how that works. There we go. Shape of ARR is 5, 1. 5 rows, 1 column. And then let's print the shape of B. Print shape of B is, comma, B dot shape. They're both 5, 1. 5 rows, 1 column. That's terrific. They match. So I can assign one to the other. And the assignment statement will cause a replacement of the first column in A with B. Or you could say the first column in B, even though we know there's only one column. The last thing we'll do is just try to break it. So let's break B. Let's make B the wrong size. And let's see if Python throws a fit or just goes ahead and does the best it can do. Let's find out what would happen if B only has 4 rows. The shapes don't match anymore. When I print these two shapes, they're not going to be the same. They're not going to be 5, 1. A is still 5, 1, 5 rows, 1 column. I'm sorry, the sliced version of A is 5, 1. The sliced version of B, or just B by itself, is going to be 4 rows and 1 column. And this might fail. Our question on the table is, what will it do if one side of the equal sign, if one side of the assignment is not the same shape as the other side? And let's try it. Got an error. Could not broadcast input array from shape 4.1 to shape 5.1. There you go. There's another error message for you to mentally process. It tells you what line of code caused the error, and you may have to Google that. It's a little bit weirdly worded, but now you know that if the two shapes don't match, we are unable to do that assignment of one array to another. And that needs to go back to what it was, Control Z. Let's try something else. What if these are floating point numbers? What if the type of one NumPy array is different from the type of the other NumPy array when we try to do this overlay? Remember, NumPy arrays are homogeneous. All the elements are the same. Now, they all may be strings, which means you can store pretty much anything, but when we're generally talking about NumPy arrays, we're talking about numeric values, so they're generally all integers or all floats, or some type of float or some type of integer. But now they're not. The original array will be integers, ARR, by default because we stored 30 integers into it. The B array will be floating point numbers because we stored floating point numbers into it, so it will be a different data type. Again, we're concerned about what happens right here. Let's find out. And what did it do? It took the data type of the target, ARR, and it converted all of these B values that were floating point numbers into integers. So we may be looking at a precision loss if we're not thinking about this when we do it. And let's demonstrate the possibility of a precision loss by putting decimal places on these numbers. B array is still a floating point array. However, when we convert or overlay that thing into ARR, what will it do with the decimal places? Let's find out. We lost them. We went from 100.5 to 100. We see then a precision loss simply by doing that overlay function. And no warning, no error message, no indication that we lost data, but we did. It's one of the risks of the profession is constantly being aware of losing data by truncating or converting from one data type to another. I think that's all of our slides. Yes, it is. Thank you for watching. See you next time.